What if everything people thought they knew about nuclear power was wrong? China's small modular reactors prove that nuclear power doesn't have to be massive, dangerous, or slow to build. The Ling Long One operates for 60 years with passive safety systems that prevent meltdowns automatically, no human intervention required. These reactors are a tenth the size of traditional nuclear plants, but deliver the same clean, reliable power that solar and wind simply cannot match. So how exactly did China turn a century-old idea into modern power plants? While the world argues over solar panels and wind farms, China quietly built something that could change the future of clean energy, a radically different kind of nuclear reactor. Traditional nuclear plants are slow and expensive. The Vogtle plant in Georgia, for example, took 14 years to finish and cost a staggering $34 billion. France and Finland have even worse delays and budget blowouts. At that scale, nuclear seems out of reach for most countries. Part of the problem is perception. People think nuclear means giant towers, massive concrete domes, and decades of construction. And honestly, they're not wrong, because the industry has been stuck using the same basic design for over 50 years. Each plant is a custom build. Concrete is poured on site. Components are installed piece by piece. Every delay adds millions, and every new regulation stretches the timeline even further. But what if nuclear worked more like plug-and-play tech? That's the promise of small modular reactors. These are pre-built reactors assembled in factories, shipped out like oversized batteries, and installed in just 3 to 5 years, cutting traditional build times by more than half. Because they're tested in controlled conditions before leaving the factory, there's less room for costly surprises on site. Here's how they compare. A traditional reactor generates 1,000 plus megawatts. SMRs produce between 50 and 300. That may sound small, but it's right in line with what many cities and industrial zones actually need. A coal plant, for example, typically outputs around 600 megawatts. SMRs hit the sweet spot for smaller regions and countries that can't support massive grid infrastructure. And they're modular. Need 200 megawatts? Install one unit. Need more later? Add a second, identical one. That kind of scalability is a game changer. It means energy capacity can scale gradually, adding one unit at a time instead of overbuilding for future demand. And because each reactor uses the same design, maintenance becomes more efficient, and training operators is far easier. Today, more than 80 SMR designs exist around the world, but so far only China and Russia have operational models connected to the grid. The US has one licensed design, but construction hasn't started. Europe is still in the prototype and safety trial phase. Russia has experimented with floating SMRs, but their land-based deployment is limited. China, on the other hand, isn't experimenting. They're building. They've already deployed multiple SMRs and have the manufacturing muscle to scale them fast. This is a total rethink of how nuclear power can work. SMRs solve 4 major problems at once. They cut costs through factory production, shorten timelines through standardization, right-size output for smaller grids, and use passive safety systems that don't require complex intervention. So how did China move from prototype to real-world deployment so quickly? To understand that, we need to look at the specific reactors they've built and what they've quietly pulled off while the rest of the world was still debating. 2 reactors in China are already doing what the rest of the world thought was impossible just 5 years ago. The first is the HTR-PM, a groundbreaking design that completely reimagines how nuclear reactors work. Instead of relying on water for cooling, it uses helium gas, and instead of fuel rods, it uses uranium pellets coated in protective layers and formed into graphite balls about the size of tennis balls. This design is called a high-temperature gas-cooled reactor with a pebble bed core. It might sound simple, but it's the result of decades of high-level engineering. Each tiny fuel pellet is coated in multiple layers of ceramic and carbon to contain radiation and heat. Thousands of these pebbles are packed together inside the reactor core, where helium gas flows through them to carry away the heat. Here's why it matters. Unlike water, helium doesn't become radioactive. doesn't corrode parts and stays stable at high temperatures. It also doesn't carry nearly as much heat, which ironically makes it safer. It can't flash boil or explode. The graphite pebbles also double as neutron moderators, slowing down the reaction and keeping everything under control, even without power or operator input. This passive safety is what makes the HTR-PM so revolutionary. And this isn't a prototype. 2 HTR-PM modules, each producing 105 megawatts, began feeding power into China's grid in 2021 and reached full commercial operation in 2023. Together, they generate 210 megawatts of clean electricity. They were the first land-based small modular reactors ever connected to a national grid. Each reactor runs independently, but they share support systems like power conversion and cooling. That modular setup means one unit can shut down for maintenance while the others keep running. The second reactor, Ling Long One, takes a different approach to small modular design. It's a 125 megawatt pressurized water reactor designed to last 60 years, and it enters production in 2025. Unlike the HTR-PM, Ling Long One uses water both as coolant and neutron moderator, just like traditional nuclear plants. But it's packed into a far more compact system. The water is kept under high pressure to stop it from boiling as it absorbs heat from the reactor core. That heat is transferred to a separate water loop, which turns to steam and drives turbines. Same process, smaller footprint. But the engineering upgrades are where it gets interesting. The Ling Long One uses canned motor pumps, which enclose both the pump and motor in a single sealed unit. That means no external seals to leak. One of the main failure points in older reactors. And its passive cooling systems can keep the reactor safe even if the power goes out and no one's around. It simply cools itself down without any active intervention. In 2022, the International Atomic Energy Agency completed a full independent safety assessment of Ling Long One. That made it the first small modular reactor in the world to earn official recognition from the IAEA. No other SMR design has cleared that bar. These aren't experimental projects. They're live, revenue-generating reactors operating under real-world conditions, and they prove that small modular reactor tech isn't just theoretical. It's here, it works, and it solves many of the public's biggest fears about nuclear energy. What's more, China achieved this using 2 completely different engineering pathways. That's a sign of both technological leadership and strategic depth. And it's something the rest of the world is now racing to catch up with. What makes these reactors truly revolutionary is this: the worst-case nuclear disasters we fear simply can't happen with these designs. And it's not just because of better engineering. It's because the physics won't allow it. In traditional nuclear plants, cooling systems rely on electric pumps and human intervention. If those systems fail, the reactor core can overheat fast, sometimes catastrophically. That's exactly what happened during the Fukushima disaster in 2011. A tsunami knocked out power, backup generators failed, 3 reactors lost cooling, and then came the explosions. But small modular reactors are designed to make that scenario impossible. They use passive safety systems, cooling mechanisms that activate automatically, without electricity or people. These systems rely on basic physical principles like natural convection and gravity. When temperatures rise, hot water naturally rises with it. Cooler water sinks to take its place. This creates a continuous flow that cools the reactor without any mechanical assistance. Above the reactor core, emergency tanks sit filled with cooling water. If things get too hot, gravity pulls that water down into the core. No pumps required. It just works automatically. And as the reactor gets hotter, something remarkable happens. The reaction actually slows down on its own. That's called negative feedback. It's like a built-in thermostat for nuclear fission. The hotter the system gets, the less reactive it becomes. Traditional reactors also have this feedback effect, but SMRs are designed to amplify it. The result is a self-regulating system, one that resists overheating by design, not just by human control. Take pebble bed reactors, for example. In these systems, the fuel is shaped into small spheres, each one wrapped in ceramic and carbon layers that can withstand extreme temperatures, up to 1600 degrees Celsius. If the core ever overheated, the radioactive material would still remain trapped inside these protective layers. That's thousands of miniature containment chambers working together to prevent a meltdown, even under extreme conditions. And while it's true that some SMR designs produce slightly more nuclear waste per unit of electricity, the trade-off is that the waste is better contained. Researchers also developing ways to recycle and reuse spent fuel. For now, the focus is on safety, and these designs deliver. By physically preventing meltdowns, SMRs offer a level of security that traditional reactors simply can't match. So when people ask what makes SMRs safer, the answer is simple. They don't rely on people to prevent disaster. They rely on the laws of physics. No power? No problem. No operator? Still safe. The reactor can't melt down because its design and materials won't let it. That kind of safety is more than just a technical upgrade, because the countries that can roll out these reactors at scale will have something incredibly rare: clean, carbon-free energy that runs 24/7 in any weather with no meltdown risk. That's not just good nuclear design. It's a new kind of energy independence. China's head start isn't just about technology. It's reshaping the global energy map. Countries looking for reliable, carbon-free power are now forming long-term partnerships with China, drawn to its proven reactor designs and factory-built systems. These deals don't just include the reactors themselves. They come bundled with decades of fuel supply, maintenance, and technical support. The message is clear. SMRs aren't hypothetical anymore. China's HTR-PM and Ling Long One show that small modular reactors are already working, safely, efficiently, and at scale. And if they continue proving faster to build and easier to deploy than traditional nuclear or even massive solar and wind projects, they could redefine how we think about energy security. So the real question is, can the rest of the world catch up in time? If you want more inside looks at the technologies reshaping our future, hit subscribe and ring the bell. We do deep dives every week. Will SMRs lead the clean energy race, or will another contender overtake them? Drop your thoughts below.